So let's talk about Cheater's Hangman. Okay, I've gone ahead and started recording. Okay, so let me go ahead and share my screen. One of the other reasons I grabbed this laptop is because of the touch screen. So the Cheater's Hangman, right? You've done that before. Objective of the game is to create a game of Hangman where you're playing against where the computer is the one choosing the word. Okay. And then the player needs to guess words and try to win the game. The twist, of course, is that with Cheater's Hangman, the player is going to lose the vast majority of the time. Now, in order to cheat successfully, for this program to cheat successfully, it has to be undetected when cheating. Okay, so this means that so essentially what we've got here is like as I put in my first example, let's suppose that we're playing with 4-letter words. Okay. And this is what's been revealed. And the player has already guessed a couple letters like E, I, U, and let's say they've also done a couple more guesses. Okay, D, S, and R. Okay, and suppose they're on their last guess. All right. Now, in the English language, there are only 3 words that will fit this, that can fit this pattern. They are goat, they are goal, and they are goad, right? To goad into action. In other words, to taunt somebody and move them into and make them do something. Now, of those 2 answers, now of those 3, only 2 are valid, right? Because we have a D over here that's already been chosen. So effectively, if this is the last player's in our program, if this is the player's last move, the player's last guess, they are going to lose, guaranteed. Because if they guess T, we are going to say, "Oh, so sorry, the word was goal. I was thinking of goal the entire time." And if the player guesses L to go for goal, we're going to say, "Oh, I'm so sorry, I was thinking of goat." Okay. Now, when we actually run this, I highly recommend doing 8-letter words. This is because I have a specific series of guesses that can demonstrate that your cheating is working correctly. Because if you follow the algorithm I suggest, it's not a randomized behavior. It's very deterministic what the moves it will check. Also, with 4-letter words, we avoid any kind of unintentional hilarity from the computer accidentally choosing a 4-letter word from the dictionary. I did give you a dictionary file, and it is time for us to be adults and talk about the Scunthorpe problem. Just an aside here, okay? It's one of my favorite asides, by the way. So the Scunthorpe problem is a problem in computer science and filtering and censorship. E.g. here, suppose you want to sign up with an email account and then they say you can't because that's an inappropriate name. This happened to a town of Scunthorpe, which is a town in London. And the profanity filter prevented them from registering their town because a substring in that word is a profanity. So, I mean, you're adults, you can see which one that is. In a more obvious one, somebody tried to register the domain name shiitake mushrooms, which was also filtered. This is mildly hilarious, you know. So, but also like serious. There are a couple other ones. Craig Coburn had his name filtered. Could not figure that out. Anybody who has a last name Wiener, this can be an issue for. another one is that some web search results for the Super Bowl 30 were being filtered out because 3 X's is often a pornographic term, and but in this case it was the Roman numeral 30. So, you know, so these things happen a lot. And you know, it's tough. You do want to make sure that you're, like, if you're building a community or something, you want to have some filters in place. Like, you don't want, you know, you especially don't want people to use ethnic slurs as the usernames. It can create the opposite message of inclusivity. But at the same time, like, the more you try to filter out, the more false positives you're going to get, which is tricky. So this happens a lot. But in October 2020, a Twitter profanity filter blocked the words bone, pubic, and stream from a paleontology conference, which I just find hilarious because paleontology, as you know, is all about bones, dinosaur bones, which are the best ones. So, but like, this happens a lot. It's because typically the way it works is that if you want to do it quickly and efficiency, what are you going to do? You're going to have some forbidden words, and you're going to say, if this forbidden word is a substring in this, you know, in this username, we are going to filter it. Which, as we can see with Scunthorpe, creates issues, right? And here in Wikipedia, that has regular, it's using regular expressions to do that. At least Wikipedia does have a way of getting around it by just doing the request the account. So they have a blacklist, but you can whitelist certain usernames just to make it, which is probably the best way to go about that. If you want to make sure, if you want to be really strict about what you're doing, especially if it's something that you are wanting children to use, which is another consideration. And the consideration, if you are ever put in this kind of position, are you building a filter, is to just know that if you are building a filter, you are going to have false positives. It's just the way it's going to work. If for no other reason, even if you're very clever about all the things in your language, what about the things in other languages? So that can happen. So anyway, this is just a roundabout way of me saying that I'm lazy and I don't want to go through the dictionary file to remove anything that's possibly objectionable. So so if you want to avoid any kind of interesting results with the dictionary file, use 8-letter words. Don't use 4-letter words. The 4-letter, and again, I could go through and remove them, but I mean, I feel like it's a dictionary file. I want it to be I want the computer to have literally access to every single word in the dictionary. Now, what is a dictionary file in general? A dictionary file, which is a file that's stored on a computer used for spell checking. Doesn't contain definitions in this context. In this context, it's what the computer will use for spell checking. You can, if you're using a Mac, you can find it in, I think, /usr, so /user /share/dict, the dict folder. But, and then English, I'm not sure where it is. Various programs use their own ones. So anyway, continuing on, the way my typical test works for this program. Okay, let me just give. The way my typical test works for this is I will give you an 8-letter word, or I'll ask for an 8-letter word. Can't count today, apparently. Okay. 8 letters. Okay. And then I'm going to make the following guesses. E, A, I, N, G. And what I'll expect to see if and only if you're following the algorithm and strategy I give you, which is not required. But if you're following the strategy that I give you, this is what I'm going to expect. Wrong guess on E, wrong guess on A, correct guess on I, N, and G. And this is because of the way the algorithm will work, which is that there's a lot of work, which is that the algorithm I suggest, and the easiest one to write, is make an algorithm that's basically scared of commitment. It doesn't want to commit to any particular answer. It doesn't want to commit to any particular word family, and so it goes for the biggest word family at all points. Basically, what it's saying is that if I've guessed these 5 letters, this gives me the most options. There are a lot of 8-letter words that end with ing. A lot. And so it goes for that. So now, how does this algorithm work? Well, it's based off of word families, okay? And so if you check out your document, basically you'll see that the function, I provide a function called create word families, okay? Or I create a stub of a function that you need to fill out that contains, it's called create word families, and it takes in 2 things: word list and all the letters that have been guessed so far. The first is just a list, obviously. The list of, and everything in the list is the same letter because that's the first thing we do. The second is what is a hash set. And for those of you who haven't checked out sets yet, it's fairly straightforward. If you've seen a mathematical set, you've seen a hash set. Simply put, it's a list where order doesn't matter, so it's not a list, okay? But it's a collection where order doesn't matter, and you can have only at most 1 copy of anything in there. It's very good for basically saying, have I seen this thing yet? Okay. And so what we need to do is we need to use categorization. Basically, we're going to split this list up into families. Okay. Now, as I've mentioned, a hash set, or as I've mentioned in video, as I mentioned in the videos, hash maps are basically used for 3 things: key value lookup. Here's the customer's account name. Give me all their information, right? Given a unique identifier, give me everything that's related to that unique identifier. Key value lookup. That's typically used in kind of database kind of situations. The second case is counting, where I don't know what I'm counting, but where I need to count all the things, like I need to count all the occurrences of all the words, the frequency of all the words in this document. So when I see an A, I create an entry for it and say I've seen it once. When I see this, I create an entry for it and say I've seen it once. If I see this again, I update this so that I say I've seen it twice. Okay, and the third case, which is what we're going to use here a lot. Now, typically we'll use the second case on exams because those are easier to write. And we're going to do the third case here, which is categorization. Categorization says, given this, here's a list of all the things that belong to this. And in this case, that's word families. So here's how it would work, okay? So let's go ahead and do I'm going to go ahead and work with 4-letter words, even though I said that's a bad idea here, but that makes it easy. And I'm just going to say that let's pretend that our dictionary only holds a subset of all the 4-letter words that are out there. Let's say there is, as we had before, goat, goad, goad, goal, gong. Let's go with fail, pail, the other pail, male, the other male, and let's go with and let's do one with E in it. Seek. Just for kicks, we're going to do the other seek. Like my homophones today. Okay. So suppose this is the entirety of my 4-letter words, okay? I think 11 should be more than enough for this, okay? So let's pretend somebody is playing. So let's go ahead and let somebody guess a letter. Let's go ahead and pretend the player guesses what? Any suggestions? G. Okay, so what we're gonna do here is that we would take in our list, which would be all these words, and our guesses would just be a set that contained a single letter, G, because that's all that's been guessed so far, right? So at that point, what we got to do is that we need to split this up into what we call word families, which is that basically, if this was the word I was going to choose, what would be revealed based on the guesses? So for instance, goat would have revealed, if we went with goat, it would, if goat was actually our hidden word, it would reveal this. And so that's what we do for basically every single word. We say goat, goat also would look like this. Goal, so would goal. So would gong. Gong would not look like that though, right? What would gong look like? Yes. Yep, G at the beginning and the end. It's a member of a different word family because the G's have different occurrences, right? It shows up in different places. So it's not just the number that matters, it's the positioning. In fact, it's the positioning that actually matters, not the number, okay? And then all the rest of these words, fail, pale, male, seek, none of them have G in it. So I'm just gonna go ahead and actually pretend that that's what we wrote over there, right? And that would just simply be dash, 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 right? So this is our, so in this case, in our dictionaries, our hash maps, our associative arrays, our hash tables, all names for the essentially the same thing. This is our key, and the value is this list over here. Okay, so we've separated this. So basically we have 3 options. We can pretend, and these options are mutually exclusive, okay? Because if we go back to our initial example of playing with this, if the user guesses goal, like going back to our initial example, if we guess goal, sorry, if the user guesses L to guess goal, we have to say goat. We can't say goad because they've already guessed D. And if we say it was goad, they'd go, you're cheating, or this program's broken, which is even worse for some reason. Right, so over here, these are mutually exclusive choices. I can't go, if I go with, I can either say you didn't get anything right, okay? Or, oh, there's 1 G here, or there's 2 G's here. Now, obviously going with 2 G's would be problematic because we'd have only 1 word and that lock us into a choice, right? We'd not be able to quote unquote dodge any guesses. So not gonna choose that one. In fact, what I'm gonna suggest is the easiest strategy to do is to choose the category, the word family that leaves you with the most choices. So in other words, it would be this one. That said, like there are other valid choices, like you could really do like kind of a lexical analysis and say, I want to choose the word family that has the least common words in it. Or, you know, all those words with X's and Z's, I'm going to count the number of X's and Z's in each family. I'm going to choose the one that has the most X's and Z's in it because X's and Z's are really uncommon. You know, they really throw you for a loop. Okay, these are valid choices, but the way I'm going to assume like what we did for over here is that you choose the most common word category. So what's going to happen is that we basically say this is going to be the new list for the next turn, and this is going to be the new state of the game, which happens to be the same as the old state of the game. Now, if your new state is the same as the old state of the game, nothing changed, that means the user made a wrong guess. So I'm going to go ahead and now erase all of our extraneous information. Except that if it's a 0, if I've drawn a circle, it doesn't want to erase it. Okay, so we've got this. So now let's go ahead and choose another. Let's go ahead and walk through this again. What other letter should we want besides G? We've already guessed G. A, I, S. If we do S, we would split it up into these words. S, we'd split it up into seek. And seek would go into one, seek and seek would go into one word family, which is S blank, 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 right? And then everything else would go into the blank, blank, blank word family. And we'd just choose this one. Okay. And now, so if the next turn we then choose L, if we chose L the next turn after that, we'd end up with blank, blank, blank L for fail. And that would also be pale. But the homophone pale for he just went pale with horror would go here. Male would go here. And then male, the gender, would go here. And then we would choose the bigger one again. Okay. And this just keeps narrowing down. And the idea here is that you'll keep narrowing down your choice. Now here, notice that the user is going to get something right regardless. Okay. Now, even if there's a chance to dodge, we don't always dodge. That's what happens in my example output over here. This one. Okay, which is the guess E, then guess A, then guess I, and then guess G. So what happens here? So I'm working with 8-letter words, and as it turns, and this is the entire dictionary. And as it turns out, there are more words without any E's than there are with E's in any specific position, right? Because while there may be more E's possibly in 8-letter words total, they're all distributed by having E's in different positions or having multiple E's, right? And so it's overpowered by the category of having no E's. So, and the same with A. There's more words without an A than there are A's in a specific situation. So we filtered out all the words with E's and A's in it. But once we get to that point, if we guess I, well, there are a ton of words that end with ING, and there's a ton of words that end with ION. So, and that combination basically is bigger than any other combination of 8-letter words once we're in that state. So that's why when we guess I, we'll guess this. Okay, now given this, with an I in this third to last position, there are more words with ING than ION. So when I guess N, it's going to compare and go, well, I guess I'm going ING. So it'll be 2 wrong guesses followed by 3 correct guesses. Once you get to this point, it becomes a very interesting game because the guesses you make really do can really lead to interesting words. Like one interesting word that, so for instance, you'll end up in this situation with that as a word, clubbing, or flubbing as a correct word. Knocking is another word that I've seen pull up. Shearing, well, not shearing. Shearing wouldn't work because E and A would have already been guessed. So that's a good way to test this code out. Now again, so you'll want to make use of word families. Okay, so essentially, and before we even do word families, the first thing you'll want to do to make sure that you can get your hash maps working correctly is to read the file and then split everything up into a dictionary file. Sorry, split the entire dictionary by letters. Okay, and I'll show you what I mean by that. Okay. So again, the dictionary file is over here. You can just download it. I call it words.txt. But did I not include the file? Give me a second. So I guess we don't have a file. That's okay. Easy enough to just simply write one. Easier to show it in IntelliJ though. Okay, so great, you've got me writing code in class for once. Well, although it's going to be method stubs. Primarily. So here I am referring to code. And now I remember that I don't have it for here. It's for a different class that I do that I provide code. So let's just go ahead and new let's just go ahead and add over here new Java class Hangman. Now, unlike a lot of ones that we do, this one is going to be done a lot. A lot of this will be done in main, but that doesn't mean you don't want to split this into a couple things. For instance, public. So the first function you should probably work on is something like this: public static map integer to list of strings. In case you want to work on a reduced file size, you can we'll just functionize this. So let's go ahead and I'll enter. So here what we've done is that this is going to return a dictionary file. It's going to create it's going to read the dictionary, and what it's going to do is it's going to return a bunch of lists. Not a list of lists, but a hash map that has lists. And the main reason I have this as set up as a function is so that you can understand how to work with maps. Okay, and what you're going to do here is that we are going to open up this file, right? And scan it using scanner. Okay, that's no biggie. And what we're going to do at that point is that we are going to read each item. This is easier than reading in the this is a much easier reading job than the Shakespeare one, because a dictionary file is one word per line. So you're going to read one line at a time. That's going to be your word. And then what you do is that basically you count how many letters are in it. Okay. You count how many letters are in it. And that is the category that it goes in. So what you're going to be doing is you're going to be categorizing these words by size. Okay. So here we're going to categorize the words by size so that we only have to read the file once in our program, right? Because we want to be able to ask the player if they want to lose again, you know, and if they want to lose again, then we're going to need to choose a new word list from the very beginning. So this will have all of our initial word lists. So if they choose an 8-letter word, we can just simply say, hey, words by size, get 8, and that will give us all the 8-letter words, right? So that's what we want. So that's basically the first function that we're going to use that has a hash map. The second one is the one that I spent the time talking about, which is the public static map string list of strings. Create word families. And again, the reason I want to go, I go this is so I tell you what you need for your arguments, because a lot of students will put in too many or too few. List of string word list. So the current word list that we have, in other words, our current mental word list of all the valid words that are possible or were possible before the user made their new guess, which is contained in set of characters or string, it doesn't really matter. And then what we'll do over here is we'll take this monstrosity, let's just call it families. New hash map. Return families. So basically what you're going to do over here is that you're going to do what we were doing in the whiteboard, which I closed for some reason because I am a genius. So good at working. All right, so and here, what is the key? The key in this case, the string key, is this thing on the left, which is what we would show to the user if we went with this family on the right, the family being a list of strings, right? So that's how categorization works. It's the category, whatever the category is, that depends on function to function. List of strings over here is all the words that belong to that category. So what you want to do is figure out, it's easier, and I might also just simply public static. This might help you break it down a bit further. Public static string figure out family. I know it's not the most, but it makes more sense than calling it get, because we have methods called get, rather than calling it get family or something like this. We want to figure out what the family is for our string. It doesn't sound very formal, but honestly, it gets the point across better than anything else. So given this word, I want to figure out what, and all the guesses we've made, I want to figure out what family that would go into. And the reason I do it like this is because that avoids a lot of awful loops. A lot of indentation. So in other words, so let's figure out, and then this should help you get started, which we get string family is equal to an empty string and return null. This is actually surprisingly where return family, not return null. This is surprisingly where a lot of people struggle. This part particularly, like, how do I figure out what the family is? Well, simply put, if my guesses are, again, if my guesses are like G, if my guesses are, sorry, need to make sure I've got a comment. If my guesses are G, G, O, and A, and the word I have is goal, I'm trying to figure out what the family is for that. What I need to do is I iterate over through it and I say, hey, is G one of the guesses that's been made? If so, then G should be revealed. same with O, and same with A. Is L one of the guesses that have been made? No, so it should not be revealed. So instead I do an underscore. So you just got to iterate through that string and basically say, hey, if it's a guess, show that letter. Otherwise, put an underscore in its place. Make sense? Okay. So that helps with a lot of that. And I'm going to grab this one more time, and I'm going to create two more methods for you to work on. So here it's going to be, I don't need that right there. Public. This one's another public static string. Public static string. Get best family. This takes only one argument, which is the word families. Of those, this is the family. Of those, this is you figure out what the key of the family you want to go with is, right? String best family, right? Put it through like a game show or something, and you figure out what the best family is. Preferably something with like Drew Carey. Okay, so like you figure out which the best family is though and this is where you can really add some personalization to your particular type of cheating, right? My particular the way I suggest is just simply go with the biggest. So you figure out which of these families has the most items in the list, right? But you might decide you want to be a bit clever and really make sure that Professor Rosen can lose, because I've gotten fairly, having played this variation of the game multiple times, I've gotten fairly good at making sure I can edge this into a case. Right. One, because the game then becomes, how can I like corner your algorithm? Right? Can I corner it in like with only 10 wrong guesses? Okay, which is really hard, let me tell you. And finally, the final method that you're going to need to write. Main. Pretty much the game can be done in main, or you can have a separate function that runs an individual game. But definitely what you're going to want to figure out first is the whole read dictionary. Can I read this, and then can I split it up into the appropriate files? You do have until November 7th to do this, although I believe our exam will be, as I mentioned, our exam will be on the 5th. Expect again on the 4th for me to go to do a run through of the practice exam, and I will release the practice exam next week. The practice exam, let me just pull that up for a second so you can have a very good idea of what you will expect, because the last thing you need in the middle of a pandemic is more anxiety, right? Or wait, do you need more anxiety? I forget. You need less anxiety. That's right. Okay. So over here, let's just take a look at the practice exam I have. And I'm sorry I'm lecturing for so long today. I just really want to make sure that you guys know, I want to set you guys up for success. So this first page on the practice exam is very representative of what you'd see as the first couple questions on the actual exam, which is, here's a bunch of data structures. Here's the scenario. Tell me which one is the best one for the scenario. And I like this because it's kind of one of those, it's not just, you're not just memorizing data structures, you're figuring out which one to use. Also, I can throw this into an auto grader by making it multiple choice, which is what those will be on the exam, multiple choice. So which of these is best for scenario? There's going to be questions on a tree vocabulary, and those are going to be a lot like the tree quiz, which is, here's a picture of a tree. Here are the nodes. Please tell me what the relationships between the nodes are, you know? So then I will test you on tree operations such as add and remove. the way this will work, because again, online, rather than making you draw, is that I will have, here's the image of a tree. This is what I'm adding to it. Please select from the following, which is the appropriate tree. Same with delete. I'm deleting this node, or I'm deleting multiple nodes. Please select the resulting tree. Again, multiple choice, just so that it can be graded very quickly. And also because I put a lot of work into making those trees in LaTeX, and thank you very much, that took a lot of time. Similar for heaps, same kind of thing for heap. So you can see a lot of like, please show me that you understand how the algorithm worked questions, but not necessarily showing you that don't necessarily rely on code. About 60 points, 65% of those points of 100 are those kind of questions where you don't need to actually code anything, you just gotta understand the algorithms. There's a Huffman coding question. And then when we talk about the coding questions, which I know that is where most people are afraid of, there are questions like this, where basically here's a tree, given the root of a tree or subtree, calculate something. Like here, I want you to calculate the size of a tree. But you can't use the size method. Please forget that it exists, or the save size variable. Please forget that that exists. I want you to write your own way of calculating the size if we aren't keeping track of it, which can be done in like one line if you are really aggressive about it. Here's another one, is full. I like using like functions that say, here's the property of here's like a word that describes a special type of tree. Can you write a function for me to see if this is something that this tree fulfills? I'm not going to do it for complete because that you can't really do that recursively. I try to focus on being able to do recursive. So, but is full is pretty good. And then here's an extra practice one, which says is an equals problem. Says, hey, can you tell me whether these two trees or subtrees are equal? On the exam, I will be using one question, essentially one tree question, but I'll be splitting it into two questions. So I'll have you, so you're going to be basically writing two functions. One is you're going to be writing a helper method and you'll get credit for that. And then on the second part, we assume the helper method works and you're going to use that helper method to write the actual method. Make sense? Okay. And then finally, I'll give you a question on the map. It's fairly straightforward map question. Just basically give me a count of something. There will be some kind of analysis question, but not as it and it will be on trees, basically just like, hey, it's not as easy as like compare and contrast like we did last time. This is more along the lines of, this is a different tree that you haven't had exposure to. Please apply the knowledge you've acquired to figure out what's special about this tree and how it works. Or maybe it might be something for hashing functions and something similar like that. But the point being is that some can be like, here's something similar yet different. Please show me how it's different. And does it being different actually matter? That's the other thing. Like a lot of changes you can make to hash state, like again, like chaining, and if you haven't watched it yet, we've got chaining and open addressing, two very different ways of creating hash tables. They run effectively the same runtime, so it doesn't really matter. So, but in terms of a mathematical theory. So, okay, and I will be sending that out, later. All right, any questions? All right. So I'm going to stop sharing and stop recording.